it's a ubiquitous sort of idea. But let's start foundationally with the importance of what this particular class of physics means. So up to this point, we've really talked about, in a mechanical sense, a number of forces. And maybe we can kind of label them off. For example, of the force we talked about. There's the obvious one. Gravity. What else? Gravity, we call those spring forces elastic forces. What else? Buoyant forces. There are two words that do that to me, buoyant and fluoride. It's not fluoride, it's fluoride. What else? Tension. Friction. What else?
Shear.
What's that?
Shear.
Okay. Shear forces require, the strength of materials illusion right there. Shear forces usually require a friction, not always, but usually are involved in an application of friction and another force to generate them.
So what moments?
Rhymes with normal. Normal force. Yes, the moments have to do with rotational application of the torque, but no, just in a real direct sense. What else? Up to this point, don't throw things that we haven't talked about necessarily, but just so we focus on the pretty much it. Torque? Well, torque technically isn't a force. Any of these can generate torque. So torque is the application of force for the generation or alteration, rotation. Pretty much it. We can lump gas interactions, pressure interactions with normal forces. I'm going to introduce another force today. And the force is referred to as electric force. Now, here's the thing. Just kind of put this into context. Elastic force. What is it that is ultimately responsible for what we call elastic force? The stretch and the compression of solid materials? Well, that's dependent on the interaction of the molecules, the mass constituents that are involved in that physical system. Well, how do they interact? Via electric force. Buoyant force.
Normal?
Well, it's normal force interaction of all these fluid particles bouncing against them. Why is it they don't just pass through? There's something that keeps them apart. Electric force. It's the repulsion of neighboring particles that doesn't allow them to just flop over on each other. Tension. What's the distinction between tension and elastic? You just assume that there's no compression or elongation, but it's the same interaction responsible. We just assume that there's no stretch involved. That one. Friction? Well, start with normal force. What is it that's responsible for normal force? Same reason buoyant force does what it does.
Gravity.
Push-ups, man.
I don't know.
Electric force. Right? That's why a surface can support and hold another surface. The same reason that substances have tension. Interact that way. Friction. Same deal, right? press forces together, they can't go anywhere, but as they rub across, it's the interaction of those electrical charges in the two systems that are responsible. Trying to see where I'm going with this, I suspect. Shear forces usually are involved in one of two ways. You take a substance and put it on a surface where it's fixed, and then you either press on it so that you can generate a force one way, and then you get the frictional interaction, which will result in some sort of an elongation that is normal to the normal forces, if you will, tangential to the surface. Or you could take two handles and push on them, in which case it wouldn't necessarily be friction. A lever that is incapable of supporting mechanical arm, for instance, subject to shear forces. But regardless, they all involve or are related to strength of materials. The strength of materials is determined by the molecular mass density and the interaction of the molecules that are stacked up at said density for that physical system. So, kind of get a sense of the significance here. We have this, and we have this. You put gravity in a small little box. That's how significant electric force is around us. We are highly adapted to gravitational forces. If we're on a different planet that has different forces of gravity, then it affects our bone density and certain other things. We're used to this constant load and trying to support that, certainly. But in a very big picture, without the electric force interactions, physical systems can't even hold themselves together anyway. They don't even have it. So without the establishment of electrical forces on a large scale, gravitational forces are irrelevant. Not only that, when you go into a microscopic observation, gravitational forces are exactly irrelevant. That's how significant this one is. So when we talk about these mechanisms that are involved now, whether it's electricity and how it relates to solid state systems, or whether we're just talking about test particles sitting out in space interacting with other things, we're talking about a much more significant concept than our idea of gravity. And it's ironic because we can trace the origin back to the study of physics and natural philosophy to the understanding, or the attempted understanding of gravity. So it's kind of missing the elephant in the room in a lot of ways. So that's kind of where we are. Now, this idea of electric force requires participants or certain types of interacting properties. And we refer to that interacting property as electric charge. Now, here's the thing about it. With mass, we got two ways of sort of thinking about it. We can talk about mass in terms of gravity, and it's in its mass, matter, that is responsible for what we call gravitational interaction. But we can also approach mass from an inertia perspective. Pick it up, shake it, pick it up, shake it. Oh, this resists that little jolt more than this does. Wouldn't matter if I was on the moon, if I was on a space shuttle, if I'm on the Earth. The distinctions between these are going to be observable and obvious. You don't need gravity to observe mass, even though mass is what's responsible for the gravitational interaction. In an electrical sense, it's a little bit different. Electrical interaction require the presence of forces. Require the presence of electrical charge. But without electric charge, you have no generation of electric force. But without electric force, this interaction, there's no other way of observing the idea of electric charge. Okay? So it's a lot more singular and a lot harder to find. How do you know something has what we call electric charge? Take another electric charge and see if they interact. It's the only way you can tell. The interaction, that's what we call electric force. The fundamental participant or the property associated with that interaction, that's electric charge. So ultimately, the idea of electric charge is it's the physical quality associated with the generation of electrical force. So we'll sort of start there. Now, so there's one distinction between mass and this idea of electric charge. Now, in case I was remiss to say, electric force or electric charge is as fundamental to nature as matter or as mass is itself. So when we think about it as a physical property, it's at an equal status on a fundamental scale, the mass itself. However, without observation of electric force or another charge to generate it, you have no way of establishing a charge is there at all. You only know electric charge is present if it interacts with some other electric charge. And the only way you know you have two charges interacting is that if you can somehow isolate gravity and separate it. So it's subtle and it's sneaky, which is why it took so long to understand it. Now, to this end, there are two types, and this is, I'm certain, quite familiar. This is another distinction between matter, or mass, excuse me, and electric charge. Mass comes in one form. We'll say it's some number of kilograms. It's got some substance or some inertia associated with it. But with electric charge, there are two types. There are what we call positive charge, and negative charge. So there appear to be two. Now, here's one. You ever wonder where these ideas of like antimatter, heard the term maybe antimatter, where this idea may have originated? One idea originally, early on, is that if electric charge comes in two forms, maybe there's another form of matter, another charge of matter that we just haven't seen yet. Why? Maybe because when you add it to another form of matter, it maybe annihilates or does something that would allow it not to be around in a world purely of matter. So maybe it's there, there might be consequences of it being there, but we just have never seen it. But it seems like obviously it should be there because electricity or electrical charge, which is fundamentally similar, comes in at least two times. You sort of see some of these redundant ideas that physicists use to sort of establish things. Now, so we have this idea of electric charge. It comes in two forms. And the interaction between the two of these is attractive when you look at opposite types. So if you take a positive type of charge and put it close enough to interact with an opposite charge, they attract. So if I were to draw a little force diagram here, maybe I'll put little circles around this, you would have an attractive force very similar to gravity between the two opposite charges. And we'll quantify that before we leave today, hopefully. Well, this is opposite. That only has one charge, if you will, one type, and it's always attractive. So again, there's some fundamental differences between what we call the properties of matter and the properties of electric charge, even though they sort of share the same step in the hierarchy, so to speak. And certainly a repulsion, which occurs when you take two types of charge of the same type. So if you had a positive charge and stuck it next to a positive charge, they would repel each other. Or if you took two negative charges and put them next to each other, some distance apart, they would also repel. Okay, so there's a fundamental problem. So, we have a charge system. How do we know we have it? Well, if I take I have a way of generating electrical charge, and I put it somewhere, and I see an interaction that's not gravitational, I can ascertain that there was a charge that was responsible for that. If it's an attractive interaction, then I know that the charge that I generated, is going to be of the same type as the charge it's interacting, or opposite if it's an attraction. And if there's a repulsion, I know it's going to be the same type of charge. So I've got some sort of indirect inferences I can make purely on the basis of this electrical interaction between electric charges. Okay? So this is the idea then. Now, what we know about the nature of electric charge, and this sort of in a way becomes philosophical, is that to the best that we know, the total number of positive charges and negative charges in the universe are the same. We're pretty doggone close to the same. And it kind of makes some sense how a charge is produced. Well, usually you take light and it miraculously splits apart and produces two different charges, opposite charges, proton, or I'm sorry, electron, negative charge, and a positively charged electron called a positron. We use those in PET scan technology, they exist. They're relatively easy to generate. So, we'll highlight this. So as a general rule, sort of the most ubiquitous state is we say nature is neutral. If there's an excess of one of these types of charges, and the key is an excess, then we say that that physical system has a net electric charge. So the idea of net electric charge is what occurs when a physical system has an excess of one of these types of electric charge. Now, there's a significance to saying excess. I'll make it an assumption that we all sort of know a little bit about the nature of what an atom is. Got a nucleus, got a positive charge in the nucleus, and then we've got this negative charged electron that sticks around it, floats around it somehow. Well, what is it that keeps things attracted? It's the positive charge. Attracted to the negative charge of the electron region, that's what pulls things together, holds things together, stabilizes the atom in a non-quantum mechanical way. But here's the problem. The nucleus is made of protons. And each of these protons has the same charge as each other proton. How on earth do they stay together in the space that is 5 orders of magnitude tighter, closer together than the span or the space occupied by one or more electrons outside? Well, there has to be another force. So, and it has to be localized. Let's call it a strong force. Absolutely. So there are some other things going on here. It's not the only fundamental force, but just kind of keep in mind, you see the logic? If opposites attract, like charges repel, sometimes the consequences are something's missing. When that something's missing, oh, maybe we've just discovered a new force law. So a lot of our ideas of nature have sort of extended that way. It's a relatively organic, obvious logical extensions. But Now, to this, coming back, okay, so all matter has positive and negative charge intrinsically. But we normally treat matter as being neutral. When we say an atom, we mean a neutral basic unit of a particular element. If it's missing electrons relative to the number of positive charges or protons in the center, then we call it a different name. Call it an ion. When we say atom, we mean neutral. When we say missing or having excess of electrons, we say it's an ion. But the neutral state is when you have equal numbers of protons and electrons, or positives and negative charges. When you start removing or adding extras, that's where you start developing this idea of net electrical charge. Okay. Now, in a macroscopic world, the origin of this, and this is key. What's missing or what's in excess? Dollars to donuts. Electrons or negative charge. Nature is charged or has a net electrical charge when there is an over or underabundance of negative charge. Because even if you took two positively charged units of matter, two potassium ions, you put them together and say, okay, now we've got two extra positive charges. Really, what you mean is you've got two individual things, each of which are missing one of their electrons, or missing one of their negative charges. Okay, so when we talk in nature about things having excess or having net charge, we're going to talk about Q's and these things having electrical charge. Understand that the inference is on a physical scale that these are systems of matter that are missing or have excess electrons or negative charges. Okay? So again, there's some things that are sort of obvious, but then there are things that are not so obvious and they're worth mentioning. So to this end, then, let's add a couple other things. The nature of electric charge. First of all, the fundamental unit, what we call the quantum of electric charge. Typically give it a letter E, kind of like an electron. And we say that this fundamental unit of charge has a value of 1.602 times 10 to the negative 19th units of electric charge in an SI sense. And we call these units coulombs. There are other units of electric charge, but this is the SI unit. So there are two then types of naturally occurring electrical charges. And by the way, we call these units quanta of charge, because they're the smallest building block. Every additional quantity, measurable quantity of electric charge is an integer number of this quanta. So we have a higher quantity of charge by having a number of quanta of charge. So the first of these is plus E, which is 1.602 times 10 to the negative 19 coulombs, or letter C, and minus E, which is negative 1.602 times 10 to the negative 19. Now, normally we attribute these two types of charges to the electrical charges associated with the subatomic particles that constitute the atom itself. So in the most naturally occurring sense, we say that the positive E is the electrical charge associated with the proton in the nucleus of the atom. And negative E is the charge of an individual electron. Now there are other things that have electrical charge. Okay, I'm not going to get into it. There are negatively charged electrons, called positrons. There are positively charged or negatively charged protons, called negatrons, or the antiproton. So there are other forms. It's not, but just in the simplest sense, right? The harder you look, the more you'll find something. The deeper you dig into somebody's background, the more likely you're going to find something in their closet. Probably a spare pair of underwear that don't belong to them. So, yeah, it depends on how close you want to look what you find. So just keep it simple and basic. And this really ties into a lot of the chemistry. Now, by the way, we know what chemistry, right? How many of you have had chemistry? Most of you have had chemistry, right? Most people take chemistry before physics. Not everybody, but most. Well, for the matter of simplicity, because at a molecular microscopic level, you're always dealing with these unit quantities anyway. So when you have an electron, why don't we just call it an E? So whenever you have an electron charge, an electron quantity charge, call it a -1. And positive, and a positive 1. Protons have a +1 charge, electrons have a -1 charge. It's not an SI unit, but it's a recognition and an understanding that it's these quantities of basic unit of charge. So when in doubt, use simpler numbers. Okay. So to add one extension to this, when you have a system with net electric charge. In its very basic sense, and typically we use a letter Q to indicate charge. I don't know, we're out of other letters, so why not just use Q? We got C, that's a speed of light, so why don't we call it Q? When a system, a sweater, if you will, has an electrical charge, then we say that the net charge will be equal to this fundamental charge times the number in excess. Individual quanta of charge. So think about this for a second. This is kind of an interesting way of thinking about it. You've never seen this in a textbook, but just kind of think about this for a second. You got a system. I don't know, maybe this makes it more complicated, I don't know. So you got a system, and it looks something like this, and inside this system you have some number of protons, some number of positive charges. It could be inside an atom, I don't care where the heck it is, it's just, you've got some number of positive charges, and you've got some number of negative charges. The net charge in this system would be, well, I've got a certain number of positive charge, protons, E's. I've got some number of positive charge. How much do I have? Well, it's, in this case it's 4, whatever the number is. So it's the number of positive charges times this E value, right? 1.602 10 to the negative 19. There's a number to plug in your calculator to remember. In this particular case, it'd be 1/4 times whatever the E value is. And I've got so many negative charges. So the total negative charge in the system would just be equal to the number of negative charges I have times whatever this E value is. In this case, 7. So I've got minus 7E. So the implication would be that Q net would be equal to the number, maybe I should have put in excess, times whatever this initial charge is. Now, since I've got 7 of these and 3 of these, it's like having, well, times E. It's like having negative 3 E of electric charge. But here's the thing. I just now thought about this, and it kind of makes some sense. There's in no way fundamental. By the way, before we conclude this, maybe we just say this is 6.02 times 10 to the negative 19 negative coulomb. So we're looking at something like negative 4.806 times 10 to the negative 19. Okay, that would be the net charge of the system. We're just going to write it in its longest fundamental form. But here's another way of interpreting this in a macroscopic system. I'm not so sure this isn't a better way. In a macroscopic sense, okay, what is it that's responsible for generation of net charge? Why does something have a net electric charge if it's a physical system? Only one way. Got excess negative charges or excess electrons. Right? Because an atom is neutral. And the only way it's going to have a charge is if you take an electron off or add another electron back. Okay? Without changing its substance, the substance itself. Okay, so you just take a substance. The only reason it's got negative charge is you've got missing or extra electrons. Okay? So another way of thinking about this, and you can tell me if this makes sense or not, is if we immediately define E. I'm going to call this E negative 1.602 times 10 to the negative 19. Now, anytime you give something a fundamental negative value, it feels wrong. But understand the positive and negative was arbitrary. It was established by Benjamin Franklin, and he didn't know what the hell he was looking at when he was looking at things, and he probably got it backwards. So we have all of our math established in terms of this positive, negative, but it was arbitrary. It doesn't matter which one is positive. This could be walnuts and acorn. 2 types of electric charge. Walnuts and acorn. An excess of nuts. Call it a net nut. Right? But we call it charge and positive and negative. So, but if we say that one fundamental charge, the excess quantity is this number, then Q net will be exactly equal to the number of excess E's times this E value. What does the N mean now? Number of excess electrons. Right? So in this particular case, rather than trying to figure out which type of sign it is here and where you put the positive, negative, you sort of make a mental jump. What if we just do this? What if we just say that if I've got 3 extra electrons or negative charges, and each one has a negative 1.602 times 10 to the negative 19 coulomb, then that would give us our negative 4.806. We probably won't ever use that extra decimal point, but for now I'll include it, times 10 to the negative 19 coulombs. Well, that, I think that's sort of obvious. I'm going to say, okay, dude, yeah, 1 plus 1 is 2. Thank you very much. But think about the reverse. What would the net charge be of a system that had this many positive charges and this many negative charges? We play the same game, right? How many excess charges do we have? Well, I've got 1, 2, 3, 4 electrons.
Plus 3.
Positive 3.
And each of these things are missing 1, 2, 3, 4, 5, 6, 7. So I've got 7 things that are missing a negative charge. 7 things that are missing and 4 things that have them. Negative 7, which is the excess of charge of the positive, plus positive 4, because that's how many extras are on those negative charges. The net result is I've really got, well, I'm going to put it over here, the net charge in this situation, since I've got more positives than negatives, is really negative 3, because that's how many excess electrons I have. Because I've got too many positive charges, I've got an absence or a negative quantity, I've got debt of electrons, where each one of them has a negative 1.602 times 10 to the negative 19 coulombs, or plus 4.6 times 10 to the negative 19. You sort of see the logic there? I don't know if it's, especially since you go back and you read the textbook, if it will necessarily resonate. But if you treat it this way, then the positive and negative just has to do with how many extra electrons you have. And if you've got negative, then that just means you've got a negative quantity, or you've got fewer electrons than protons. And since each one has this charge, it's going to give you a net positive charge. And that's ultimately what we have here, right? Extra positive. I like thinking about it this way for one reason. It absolutely emphasizes that it's the presence or absence of those negative charges that is responsible. See where I'm coming from there? That's the key.
So number of protons doesn't change, right?
If you have a system of mass, okay, say a whole bunch of iron atoms, it will gain or lose, or it will have net charge based on how many electrons that iron has given up or added extra. Now, if you say, well, what happens if an iron atom loses a proton, for instance? Same number of electrons, but now you just take a proton out.
It's not iron anymore.
Now you've got a new substance. Now you've got all these iron atoms, and one that's not iron now, it's cobalt or something else. And that cobalt has an extra electron because it lost one of its protons. So you're still looking at matter with an excess of an electron.
Okay.
So I really don't like the idea of thinking of positive charge in a big picture as though it has some deeper meaning. It just means you're just missing these damn electrons. It's always about the electrons, and now we're teetering on the edge of falling into chemistry. But it's not chemistry, it's just physics. Oh, that's the chemistry. Right? So that's sort of the idea. Now, to build on this, okay, you take systems, they have electric charge. What's more important, though, is how do those electric charges interact with other electric charges? And we know they're not going to act with something that doesn't have electric charge, but they're going to interact with other things that do. What is the nature of this interaction? And at any point, please stop and ask, clarify, tell me, dude, what the hell are you saying? You just said two opposite things, what the hell are you talking about? Ask me. I talk, I write, sometimes there's a detachment, right? So just ask. I'm good with that. Because for me, it means you're paying attention. And I don't ever have a problem with clarifying something crazy I've said. Okay, so now we quantify electric force. So let's take two charges. So let's look at the force between two charged systems. And, well, let's make these systems. I'm going to start over here, and I'm going to call it positive. I'm going to call it Q1. Q is charged, and this is system number 1. And I'm going to say that this charge is positive, but maybe it has a value of plus 1 coulomb. Okay, now we'll put easier numbers in there. These electrons, those numbers are awful. No doubt about it. SI units for electric charge is horrible. Before doing anything else, what does this number mean? I've got Q with some positive charge. What does that really mean about this? What does it say about this physical system?
It has
It's
one less
missing
electron.
It's missing 1 coulomb of electrons, or of negative charge. So we can even figure out how many missing electrons we have here, right? How many electrons?
One.
1 electron is 1.6 times 10 to the negative 19. So we got a lot more going on here than that, right? I'm just going to make a note here that we have the number of missing electrons and electrons, if you will. There's your Ne, right? It's equal to Q1 divided by E. Q1, that's plus 1 coulomb. E, negative 1.602 times 10 to the negative 19 coulomb. So how many electrons do we have in the system? It's the inverse of this number, right? So something like 6.67 times 10 to the 18.
6.24.
Oh, 24, okay. Times 10 to the 18. Negative, right? Because we're missing this quantity of electrons. If it were in excess, it'd be a positive. Or if it were... What am I doing here? Yeah. I'm missing these electrons because it's a positive charge. If this was a negative charge, that would mean I would have an excess of electrons. So it's kind of an addition by subtraction. It's not a bad thing to note that. So in other words, I'm missing a whole zip load, this many electrons or negative charges. Okay? It always comes back to that. Right?
Okay.
People that know me thought I was going to say shit load, but I was good about it.
You still said it.
But I was only explaining what I didn't say. That's how I keep secrets too. I never tell anybody a secret, but I'll ask if they knew. You know Joe's on his taxes? No, I don't want to say anything. I'm just curious. Okay, so let's then take another charge over here and make it negative, so we got a traction here. And I'm going to say Q2 has a value of, that'd be a little bit original, so how about negative 2 coulombs? Now I'm not going to ask how many extra electrons are there because I think we're sort of beating that horse into the ground. I'm going to separate these by a distance of R equals, how about 0.5 meters? So what can we say about it? First of all, it's a two-object system. If you want to know something about the nature of the interaction between them, you got to look at one or the other. When we look at them together, their interaction is internal to their environment. And as a subtle reminder, when we refer to the idea of force, what's implied? Russell's not here to answer all these questions for me, so if you've never heard my spiel on it, when you see you've got an object and it has force on it, what does that mean? What do you think? It's being disturbed by its system or by its environment. Okay? Force means disturbance, or it's the interaction of something with its surroundings. If these two interact with each other, if I look at them together, guess what? Their interaction is internal and has nothing to do with their surrounding. So if I want to know the nature of the interaction between them, I got to look at one or the other and see what's happening to it as a consequence of the other. So let's look at Q2. What is the force on Q2? So here's how you calculate it. It's an electric force. Well, there could be gravity too, but let's just, for now, let's just look at these two isolated from everything else. We would say that the electric force, now we change the little trouble again. The definition of electric force, and it's a vector. First of all, I forgot to do this, I better do it now. Let's draw a free body diagram for Q2. I always start there. If we're going to calculate forces, we can probably learn a lot just by looking at it. So this is our